So our first speaker for today, Yanting Yin from Flinders University, who will speak about study of interface and dipole for organic-based electronic devices with a non-destructive spectroscopy analysis. So when you're ready, please.
All right. Thanks for everyone attending, and thanks for organization. In terms of hard time of COVID, everything is restricted. So today's topic, I try to give a presentation on my PhD project, which is study on the interface of dipoles for organic electric devices. For example, organic solar cells with a combination of spectroscopy analysis. So in this work, I'm not going to talk something about high efficiency or new materials, because this is not our main interest in this research, but more something like more a fundamental research along the interfaces structures. So this outline of the presentation today. First, I will talk about interfaces and interface, for example, interface importance for the organic devices, polymer-based solar cell. Then some current technologies has some drawbacks to study interfaces, and the advantage of our, let's say, our technology to study this interface and dipole. Next, that's methodology. I'm talking about some combination of spectroscopy and ion scattering spectroscopies. I would show 3 chapters, or let's say 3 individual topics, some examples of the analysis on the molybdenum oxide, forming of the molybdenum oxide and the P3HT, PCBM bicontrol junction, BHG system. And this whole interface has been experienced different treatment. For example, at the very commonly happened air exposure and different annealing process for the organic fabrication process. Next one, I will show let's say a project made by my former colleague Natalia Sumo, based on the lithium fluoride salt on the individual P3HT and PCBM, and then methodology and acknowledgement. So the first thing I will talk about, introduce a bit about interface. So on the left side, there's a basic cross-section of a perovskite solar cell. So you can see the interface is mainly formed between 2 different materials. For example, on the top side, molybdenum oxide and spiral methodology. Spiral measured processed layer. And next one is the tin oxide ITO interfaces. So what is commonly happened at the interface? The first thing is, if you put material A on material B, the mainly happened thing is because of the particle mobility, that's probably we're getting some chemical mixing of between the interface. However, along the mixing of chemical, there's possibly chemical reaction. For example, is 2 materials, probably they will react between each other, which you probably can find in front of the interface. However, that's more important thing in the organic solar cell is that that's possibly a electronic properties, or let's say the electronic reaction or interaction happening at the interface. Let's take example. For example, if you have molybdenum oxide, which is pristine, molybdenum oxide actually has a really high work function than the polymer structure, for example, P3HT and PCBM. So if you put these 2 materials together, because the Fermi level will need to be aligned, there will be electron transport. So with the electron transport, you will have a enriched accumulated electrons, and the side the electron has been flowed. So that would be definitely a dipole forming at the interface in these structures. So I will just show a very quick structure about a very typical, which we call it inverted structure, more polymer-based solar cell. That's based on a molybdenum oxide sitting on a, for example, active polymer layer. People use a range of different new materials at the moment, but in this work, it's just a very old system has been shown. Based on that, there will be molybdenum oxide forming interfaces forming between molybdenum oxide and polymer BHG and structures, and being reported by James Mayer at many years ago in the advanced materials. So everyone interested can find this, let's say, find this publication. So what happening along these interfaces, molybdenum oxide generate a really huge dipole at the interface. So this interface is actually bending the HOMO level of the polymer substrate. And the HOMO level actually can align with the conduction band of molybdenum oxide. There will be a whole obviously different charge transport mechanism in this case happening. That charge transport can happen directly from the HOMO level of BHG towards the conduction band of molybdenum oxide. However, if the dipole is not strong enough, for example, the dipole bending is not strong enough, what will happen is the HOMO level will be in the middle of conduction band and the valence band of molybdenum oxide. Then the charge transport will definitely be blocked because that's, let's say, the electronic barrier happening at the interface. So studying at the interface will be very critical to the fundamental mechanism of charge transport for organic solar cell performance. That's some examples for the current technology, as I have used some of the technology to study of the interfaces. However, both of them have quite a bit drawbacks. For example, as chemical remove or the mechanical polishing argon sputtering mechanism to try to remove material A from material B and then investigate the interface. However, what happens is you can never get a pristine properties from material B because you can't guarantee as no damage happen on material B when you introduce the different method of de-elimination. For example, if you have iron sputtering, which is considered as almost the most gentle method, the iron sputter, if you do removing iron sputter with iron sputter of the molybdenum oxide, what will happen is the oxygen actually kicking away much quicker than moly in terms of the atomic mass. So in this case, it's still really hard to study interface because we don't have an actual way to eliminate the surface layer from another layer and see directly into the interface. So in our work, what we will do is we do it in inverse way. We will do a material A, we forming material A gradually with a very tiny thickness on material B, and then increase the thickness to see what will change at the interface with a range of different, let's say, a combination of spectroscopy, which were operated in a UHV chamber. They are integrated actually. So the XPS give information about chemical and valence state of element, give us the chemical reaction if it's really happened. UPS and the MIS shows the electron properties along the valence structure, and also the work function can be determined with UPS. IPS is giving conduction electronic states, and the original microscope give the elemental distribution, which were not actually included in interpretation, but will be later for the details. And the NICIS is giving elemental depths along a certain depth from the outermost layer towards the bulk. So the first work has been published 2 years ago. It's based on the molybdenum oxide gradually sitting on the BHG, P3HT, PCB, and BHG. But the molybdenum oxide actually depositing with tiny bit thickness. For example, it's just 1 angstrom. It's even not forming a monolayer on the surface, and up to 8 nano. That's kind of like gradating, for example, 0.1, 0.2, 0.5, and 1 nano, 2 nano. So the first thing what we see from the NICIS measurement is what we see is molybdenum oxide actually is penetrating heavily into the bulk control junction. For example, if on the right side of the figure, if we only put 0.1 nano molybdenum oxide, what you can see is actually you can find moly particles in the depth of 3 nanometer. And if you put 2 nanometer of moly, the moly even penetrates much more. At least you can find 10 nanometer molybdenum oxide particles penetrating into the polymer control junctions. So this gives us a critical information. Moly is kind of like really mixing with BHG when you put molybdenum oxide on surface. So in terms of the chemical analysis, further analysis, we do XPS as well, trying to figure out if there anything happened, chemical reaction happened between moly and the polymer BHG. What we see is the molybdenum oxide it's actually not really changing. Sorry, it's the low thickness not show, but I can say the moly from 0.1 nanometer to 8 nanometer, the shape is exactly the same in terms of the shaping and the binding energy, and no chemical reaction happened on moly. However, interestingly, upon the polymer side of the carbon, for example, for the P3HT PCBM, normally we will find a main carbon peak from the polymer substrate sitting at 285. But in this case, if we put moly oxide on the BG, what we're finding is a peak is kind of like increasing with the increase of moly oxide in terms of the ratio. And this peak sitting at very low binding energy, which is only 283.6 or 7. So in this case, this carbon is most likely forming because of the formation of carbide. So in this case, moly carbide, but there's nothing of moly carbide forming because moly is not changing. So this began to introduce an information for us. Is that anything rather than chemical reaction happening at the interface? The only explanation is this fraction of carbon belong to BG is actually experiencing a electrical bias at the interface. And the electron bias seems more than 1 electron volt, but it's not accurate enough for XPS because XPS giving a depth of 10 nanometers, including a lot of bulk informations. So what we do next is a pure electrical characterization use UPS and MES to investigate what really happened on the interface in terms of the electrical bias structure. So the first thing we can see for the work function onset, let's say from a lot of publications, people will say this is the modification of work function, something like that. However, this is not exactly accurate in terms of the secondary electron distributions, but this is not in the center of the work. The center of the work is actually on the right side of the figure. What we can see from a less moly oxide on BG up to a higher one, both of the onset of the valence band maximum shifted, as well as the shape actually changed. And then we're trying to figure out, okay, this part is changing. So what really contributing to this changing? And anything else, for example, we can find from the UPS valence spectrons. So in this case, we try to introduce another method to decompose these regions. For example, the method we call it singular value decomposition, which is based on the mathematic formulas. So this telling us information. For example, once we have a measured spectron, this spectron actually consists of 3 different materials. For example, X, Y, and Z. Whatever they are layered or they are blended, whatever. For example, I have 20% of material A, 30% of material Y, else and material Z. What will happen is you will find different fractions, and for example, the spectrum from material X with its fraction, material Y with another fraction, material Z with the third fractions, and these different fractions contributing, put them together and sum them together, contributing to the spectrum measured. So this is another inverse way to decompose these spectrons. So interestingly, if we decompose, for example, this right side of the valence region, what we will find? We will find especially a moly oxide spectrum. It looks exactly the same shape of pristine moly oxide. And else we find a pristine polymer BHG spectrons, but the most interesting is we find the third spectrum. It's exactly the same shape of the polymer BHG, but in terms of, for example, the electron density states and the peak onset space. So this is exactly the same polymer spectrum, but shifted on the energy scale towards a lower binding energy by at least 1.3 electron volt. So this definitely gives us information. The polymer BG actually experiencing an electronic shift at the interface once the interface can be detected. But however, this SCBD has a disadvantage because it's only gives us the mean energy shift. Aaron, possibly Aaron knows if a dipole happened, there's a dipole moment. So if the material is away from dipole, it will shift it less. But if it comes to really close to dipole, it will shift more. So there's a range of different shifts. So in this case, we will introduce another method. For example, we allow a constitution or contribution of molybdenum oxide. We allow contribution of pristine polymer. We allow another one is the third polymer, but allowing it to different shifting with a different step on the energy scale. For example, we allow it 0.05 electron volt shift as a single resolution. So in this case, we actually can get a constitution of all the different energy shift of the BG, and they give us information of dipole, a whole dipole moment at the interfaces. On the right side, what we can see, if we only put 1.1 nanometer molybdenum oxide on surface, the dipole shift, energy shift is very less in terms of the energy shift distribution. However, if you see the 1 nano, 0.75 nano, and 2 nano, the energy shift is very sharp at least 2 electron volts. So in this case, give us a very full image about what really happened at interface. Actually, if you put a tiny bit more oxide on the polymer substrate, what will happening? It's not even forming a enclosed layer, and each molybdenum oxide particle is away from each other. So what will happening is the dipole forming is let's say a round circle is 360 degrees. So what happening is two molybdenum oxide probably encounter with each other. So the interface dipole will hardly to be accumulated, and the dipole strength pretty small. However, if you put a lot more oxide particles on the polymer BG, that will forming an enclosed layer, and that will also form a very sharp interface from the molybdenum oxide space towards the molybdenum oxide, and in between the molybdenum oxide and the polymer BG. And let's say at the interface structures, the polymer has been found shifted negatively, which means the dipole actually pointing from the polymer towards the molybdenum oxide, and molybdenum oxide on the negative end. So the polymer inside the dipole will be shifted to a negative ways. So in this case, we can actually contribute a restoring energy level structure at the interface on the right side of the figure. So on the left side here, the polymer, and the right side is actually infinity of the molybdenum oxide deposition thickness, whatever how far thickness it is. Along the interfaces, we find a range of different shifts of BG like this ways. So this gives us a whole information about the interface structures. Now we can begin to think about what is really happening on the interfaces. For example, if we have a little tiny bit molybdenum oxide deposition thicknesses, the dipole actually quite small, not enough to supporting the whole transport from the HOMO level to the conduction band, and need to be overcoming a huge electric barrier to go to the valence band of molybdenum oxide. However, if it's more than 2 nano or 1 nano molybdenum oxide deposition, that's the dipole will be strong enough to support the whole transport from the HOMO to the conduction band of molybdenum oxide. Give us a whole information about electronic structures. So next one, I try to describe, for example, a lot of people will say, okay, guys, I already put 8 nano, 10 nano on molybdenum oxide. So if I already do that, so what's your point? You only, let's say, investigate a low thickness on molybdenum oxide. However, without this fundamental analysis, you'll never know what really happened at the interface. And as well, you will never know if you do the different treatment upon the interfaces, what will happen to the dipole. So for next work, I will show what will happening if the molybdenum oxide, the whole structure is air exposed, what will happen to the interface dipole. This comes from one of my colleague who is discussing like, once the molybdenum oxide during the air exposure, device performance actually sharply decreased. What really happened at the interface if this whole structure is being air exposed? So this is also based on analysis. We do molybdenum oxide on the Buck-Hunter junction P3HT PCM, same interfaces, and expose it to a range of different air exposure time. For example, we do 5 minutes, 30 minutes, an hour, 2 hours, 6 hours, which 5 minutes, 2 hours, and 6 hours only show in the figure. Otherwise, the figure will be very complicated. So the first thing in the eye we can see with a higher exposure time, the distribution dipole actually is shifted to a less energy shift, and the mean dipole strength, which is calculated based on the distribution, actually from the 1.3 electron volt and downwards to the 0.9 electron volt, which means the dipole actually decrease with the air exposure. So we also do the XPS, and we see a relative concentration of H2O, the water from the oxygen contribution, increase. While this one increasing, the dipole actually decrease. So in this case, we understand once the interface of molybdenum oxide and bond-counter junction, even coated with coated with electrode, it's exposed to air, and moisture from air actually penetrate, or let's say invade into the interface, killing the dipole, because this is the, let's say, the non-conductive elastic. It's kind of killing dipole because dipole is electronic properties. In this case, for example, after 30 minutes exposure we have calculated, the solar cell performance might be dropping because the dipole is not strong enough to support the whole transport from the HOMO to the conduction band again. So in this case, the solar cell performance might be sharply decreased. So pitifully, we don't have the device performance, but trying to make a bit more device performance to supporting our argument. Another work we have done is actually also based on the system of dipole. So this is thermal annealing. We do 4 different type of samples. The first one, we don't do any annealing, just put moly on the polymer BG. The next one, we pre-anneal the bond-counter junction at about 150 degree and put moly oxide on. The third one, we put moly oxide on first and anneal the whole structure together. The fourth one, we first pre-anneal the moly oxide. We first pre-anneal the bond-counter junction and then put the moly oxide annealed again. So the first of our interest is doing the NICs. What we can see is, in terms of the distribution of moly oxide, with the pre-annealed sample, the moly actually sitting very close to the surface, forming a sharp interface. But the whole structure will be significantly changed with the post-annealing process. We annealed the system again, or we didn't do any pre-annealed of the polymer BHG. The moly oxide actually penetrates with the thermal annealing deeply inside the polymer BHG and forming a more mixed interfaces. Next one, we're also trying to figure out what will happen in this case of the dipole and the interface structure at the interface. So with the pre-annealed one, because most contributing is from the moly oxide, so we have the shifted polymer BHG peak sitting at lower ratio, but this peak actually is sitting at even lower binding energies. However, with the post-annealing spectrum, what do we see? Okay, we still see a quite big shifted polymer BHG peak, but they are not shifting a lot. This gives us information that's very likely at the interface we will have a very different dipole, let's say a very different dipole distance and also dipole strength. So by decomposing the UPS as well with the SVD we described, we can see the mean energy shift of the dipole actually very different of different annealing treatment. For example, we still have a quite strong dipole energy with non-annealed one and a pre-annealed sample. However, the dipole actually decreased a lot with the post-annealed. Whatever we do pre-annealed BG first or not do it, but with post-annealing, the dipole actually almost lost. So this gave us another information. For example, if we have a non-annealed interface exactly as our first work, the dipole is we call it normally formed. But if we pre-anneal the bicontour junction, what will happen? The moly accumulated on the surface. It will form a dipole. This dipole with less dipole moment. However, this dipole is very strong because they are very because the moly oxides is aggregated on the surface and the sharp interface have been formed. However, if the whole structure has been annealed, what will happen? The moly oxide penetrate, and each moly particles actually they were redistributed and they will be distant. If the moly particle distant, they will encounter with each other and a killing dipole formed at the interface. Interface might be very, very long, and the dipole moment probably very long, but dipole actually very weak. So in this case, we do a assumption with non-annealed and pre-annealed interface. The dipole is still strong enough to support whole transport from the BHG towards the moly oxide region. However, if we post-anneal the whole structure, what could be happening is the dipole is not strong enough anymore to support the charge transport. In this case, we do some device. The best performance one is pre-annealed sample because it's also getting less penetration on moly and contributing to a higher shunt resistance. So in this case, what we will see, so it's only 4%, and definitely not competitive to your guys probably doing like 10% or 80%, but it still gives us information because the device performance is definitely in line with different annealing treatments on the sample structures and give an instructive function what we should do and what we should apply for the device performance during the fabrication. Another thing I'll try to include from Charles Schumann, who is a former group member, who is doing interesting is she actually evaporated lithium fluoride salt on individual P3HT and PCBM and find a exactly same phenomenon as the moly oxide, giving us a confidence that we can apply this system on a range of different interfaces. So what she did is she did lithium fluoride evaporated from the low thickness to a higher one on the P3HT and PCBM. And in this region, what she found is actually the polymer not shifted, but in this case, actually the lithium fluoride shifted. So the work is actually inverse from mine. Oh, sorry, because with a lower thickness, it's actually closer to interface, and with a higher lithium fluoride, it's actually distant from interface. So what you can see, with a higher lithium fluoride, 330 and it's 3 nano, actually it's almost pristine lithium fluoride. And if it's come closer to interface, the lithium, both of the fluorine and the lithium XPS peak began to shift it to negative by more than 1 electron volt, giving an evidence that dipole forming actually biasing the lithium fluoride to a lower one, which means at the interface, what could be happening? And as well as she also did some UPS. What can find is
excuse me, Yanting. We just have to wrap it up fairly soon. We're kind of running out of time. So yeah, if you can quickly, yeah, thank you. Thank you.
Very quickly. Sorry for taking a very long time. So the lithium fluoride actually shifting to a lower binding energy if its investigation is coming to a interface. In terms of Nicky's measurement, what we also seen, if the lithium sitting on the P3HT, it's actually forming a sharp interface than the PCBM. So in this case, what will happening is at the interface, lithium and the polymer substrate actually forming an interface, which is pointing from the lithium towards the organic materials. So this is another information we can get applying for different materials surfaces. So I won't do a conclusion because we're running out of time. Just thanks for my supervisor Natalia and FMMA from Flinders Microscope and Microanalysis Center. Thanks. Any questions?
Thank you very much. I think this is really interesting work. You know, we often draw these layer stack diagrams where, you know, we have these sort of perfect layers, and of course, you know, what's really happening there is much more involved. So it's very interesting. I would like to open it up for questions. If someone from the audience would like to ask some questions, please go ahead. You just need to unmute your microphone.
I'm Paul Byrne from the University of Queensland. Thanks very much, Yanting, for your talk. I was just curious about your analysis of the water vapor diffusing through the moly oxide into the device.
Yes.
Can you tell whether it is water that's in the device or whether the moly oxide has reacted with the water to form molybdenum hydroxides? There's some evidence that's being published that that reaction occurs. And I was just wondering how that might affect your analysis of the dipoles.
Yes, this is one of our concern actually. Firstly, when we try to see if there anything happens on the reaction of moly oxide, if we expose moly oxide to the air, and anything like moly hydroxygen happen. However, from the moly XPS, we did not observe significant change upon the moly. The only thing from the moly is if we expose the pristine moly layer to air, it's also the moly oxide actually also getting moisture physically into it. And in this case, the moly, let's say the electro properties of moly have changed. However, the moly chemistry does not change in terms of the result showing from the XPS.
Okay, thanks very much.
Hi, it's Andrew Nelson here. There's a lot of interesting work with different structures going on here. I'd love to see how neutron and X-ray reflection would be able to characterize some of these structures. For example, we do a lot of work looking at water vapor going into various films and so on, and characterizing where the water accumulates, and also things like interdiffusion of you know, we could do interdiffusion of moly oxide and those polymer films as well. There's a lot of interesting structures there.
Well, that's a good suggestion actually. In this case, we can do a much more accurate, let's say, analysis upon the, let's say, the penetration of the H2 of the water, because the water it's actually quite hard to distinguish from oxygen of the XPS. However, we observe the increase of oxygen, but it could be from water, but we also oxidize the polymer first and try to exclude the oxidation of polymer in the additional work. But that's a good suggestion.
Yeah, so with, if you use D2O, for example, yeah, you see the D2O, change that scattering density significantly. And we can do it, you know, different humidities or different partial pressures of water.
Oh yes, that's a very good suggestion. Important one. Yes, great.
All right. Thank you, everyone. Thank you, Yanting, for the interesting presentation. I think we really have to stop there for the interest of time. So we can't really do a proper round of applause, but I'm sure that everyone would join me in thanking you for what was an interesting talk and very interesting, thought-provoking topics. So can you please stop sharing your screen?
Yeah, sure.
So that our...
Oh yeah, I find it. Stop sharing.
Yep.